Hey guys, and welcome to our physics video project. We are out here in the middle of nowhere to show you that the Doppler effect is actually a real thing, and the four of us are going to team up and show you that, along with Gary the Goose.
What is the Doppler effect? The Doppler effect is a change in frequency of a wave for an observer moving relative to its source. For example, when an emergency vehicle is moving towards an observer, the wavelengths are closer together, causing a higher frequency, whereas moving away from an observer, the wavelengths are further apart, causing a lower frequency. Compared to the emitted frequency, the received frequency is higher during the approach, identical at the instant of passing by, and lower during the recession of the source.
And now to talk about the math behind the Doppler effect. As you can see by this equation behind me, the relationship between observed frequency and emitted frequency is given by the equation here. C is the velocity of waves in the medium, while BR is the velocity of the receiver relative to the medium, and BS is the velocity of the source relative to the medium. This above formula assumes that the source is either directly approaching or receding from the observer. So if someone was standing right in front of the car and they were about to get hit by the car, this is what they would hear. Now if the speeds Vs and Vr are small compared to the speed of the wave, the relationship between the observed frequency f and emitted frequency is approximated. That's if the observer would be standing off to the side of the approaching car, which is what we will simulate later on this video. When the observer is very close to the path of the object, the transition from high to low frequency is very abrupt, and when the observer is far from the path of the object, the transition from high to low is gradual. So if we were to use an equation and calculate frequencies with an approaching car horn, we would use this equation right down here in small font, and this would give us the change in frequency. And then if we wanted to calculate change in frequency of an ambulance siren approaching, we would use this one as well. And now we will send it off to Will to give you some examples.
Our first one here, the object is not moving, so everyone will hear the same frequency. Next up, the sound source is moving with a speed of Mach 0.7. Since the source is moving, the center of each new wave front is now slightly displaced to the right. An observer in front of the source will hear a higher frequency, whereas an observer behind it will hear a lower one. We will simulate this later on in the video. Example 3, the source is moving at the speed of sound, and an observer in front of the source will detect nothing until the source has arrived. An example of this could be a plane breaking the sound barrier. And finally, for our last source, the sound source has now surpassed the speed of sound in the medium and is traveling at a speed of Mach 1.4. An observer in front of the source will detect nothing until after the source has passed. We will now simulate example number 2 for you.
Ready? Let's get it, guys. Notice on the spectrogram analyzer that the wave pushes to the left as the car passes over, showing a change in frequency detected by the iPhone's microphone.
Well, we just proved the Doppler effect is real. It's time for Gary and the gang to go home.